Coming up on Dr. Kiki Science Hour, we're talking about perception and time with Dr. David Eagleman from Baylor College of Medicine. That's up next on Dr. Kiki Science Hour.
Netcasts you love.
From people you trust.
This is Twit. Bandwidth for Dr. Kiki's Science Hour is provided by Cachefly at CACHEFLY.com.
This is Dr. Kiki Science Hour, episode 58, recorded on August 5th, 2010. What flavor is your rainbow? Welcome, everyone, to another episode of Dr. Kiki Science Hour. I'm Dr. Kiki, and this is the hour where we get to delve into science. All the scientific questions that bother your brain from time to time, we're here to talk about them. And I like to invite esteemed scientific guests to help us explore the scientific world, people who are experts in their fields. Today, we're going to explore, investigate the world of perception. So how do we really know the world is the way it is? How do we really know what things are around us? These are philosophical questions. Who am I? Where am I? They're also questions stoners ask themselves occasionally, but philosophical questions nonetheless that can be investigated scientifically. As technology advances, we find new ways to be able to investigate these questions that have bothered people since 400 AD, since Plato, since Aristotle, the old ones, the guys who started asking the big questions in the first place and writing them all down. But anyway, today to talk about perception and the science of perception, we have Dr. David Eagleman. He has joined me. He is a neuroscientist and the head of the laboratory. Let's see if I can get this right. The Laboratory for Perception and Action at Baylor College of Medicine. He's also a writer. You may have seen his book, Some, out at a bookstore or on Amazon or something near you. He's also a big thinker and calls himself a possibillion. So without any further ado, David, thank you so much for joining me here.
Nice to see you, Kiki.
Yeah, it's great to see you. We actually met a few years ago at the first World Science Festival. Do you remember, what were you doing there? I remember you were giving a talk at the time.
That's right. There was a panel about creativity and what makes genius. And so there were a few scientists, and then there were a few artists and performers and choreographers, and we were talking about how brains put together creative ideas.
And how does this fit in with perception? I love the kind of tie-over between perception and creativity. Is there a tie there?
Well, we've been exploring a tie there. One of the things that I study in the laboratory is called synesthesia. And this is a condition where people have a blending of the senses. So somebody with synesthesia might hear music and it causes them to see colors, physically see colors. So it's not simply that they are thinking about colors or remembering a learned association, but it's they're actually having the physical sensation of seeing colors. Or somebody might hear something and it puts a taste in their mouth, physical taste in their mouth. Or they might eat something and it causes them to feel something on their fingertips. So there are many different forms of synesthesia, and what they all have in common is a blending between the senses. In other words, the different parts of the brain involved in coding different sorts of stimulation are talking to each other more in a synesthetic brain than in a normal brain. And so the connection to creativity might be that creative people tend to have more crosstalk in their brains than normal people. And so this is a hypothesis that is being pursued now.
I think that's an interesting hypothesis. Is it possible that what's happening are these brain areas that are actually next to each other, and that's how the crosstalk is happening in the first place, or are axons, our synapses, dendrites, are things having to cross over large distances in the brain for the synesthesia effects to actually occur?
It's a good question. We don't actually know the answer to that. The first speculations were that it was neighboring areas had increased crosstalk. But there are some types of synesthesia that don't quite fit that model. So it does appear that even across distant reaches of the brain, different areas can talk to each other. And of course, even brain areas that are very far apart anatomically can be very close when it comes to synaptic connections. There can be either by direct or indirect routes, information can get from one place to another across the brain very quickly. So I think the grand unifying hypothesis of synesthesia, that maybe it was about neighboring brain areas, I don't think that's going to hold up in the end.
So it gets more complicated the more you delve into it. Isn't that like everything?
Yes.
It's always more complicated. Are you a synesthete? Is this where your interest arises from?
I'm not a synesthete myself, but I immediately recognized in synesthesia about 8 years ago, I recognized that this was a terrific inroad into understanding how different brains construct reality differently. So it turns out that synesthesia is heritable. And what this means is that with a very slight genetic change, you can see reality differently than your neighbor. You have a different experience of the outside world. And I've always been fascinated by issues like that. In fact, that's the thing that summarizes all the work I do in my laboratory is how does the brain construct reality? Because we know that when the brain changes, your perception of reality changes. You can get brain damage that not only changes your personality or your decision-making, but your capacity to see motion or see colors or name fuzzy animals or hear certain kinds of sounds, things like that. So we know that your perception of the world is totally dependent on the integrity of your biology. And but we don't know much past that. We don't know how it actually gets constructed. So I realized that synesthesia was a really good inroad into seeing how does a very tiny change in the biology lead to a very big change in how you see the world.
And if people out there are interested in finding out whether or not they are a synesthete, Dr. Eagleman has a battery of tests that you can take online to quickly determine whether or not you are. I haven't actually registered to find out. I'm pretty sure I'm not. I think I would know by now. Is it something that people know or don't know, or are there a lot of people who actually don't know? I mean, that seems odd.
Right. So most synesthetes live their whole lives without realizing that other people see the world differently than they do. And that's because we all accept the reality that's presented to us. So whatever your brain is feeding you, you imagine that's how everyone else sees the world. Almost certainly it's not the case. People see the world quite differently from one another. So, you know, there's this old philosophical conundrum about whether what I call red is whether what I experience as red is what you're experiencing as red internally. Because all we know is that if our mothers both teach us to call something red, then we can negotiate and transact in the outside world, but we might have a very different internal experience. So that's an old philosophical problem, but what we are doing is essentially elevating this to a real scientific problem by asking how do people actually see the world differently.
Yeah, it seems to me that we have in people who are colorblind are in that sense seeing the world. They don't see the red and the green, so they have a completely different visual spectrum in terms of the colors that they see. So their red, like you said, is probably a shade of gray or brown or something that is similar.
That's right. And so until they learn about the concept of color blindness, they're accepting that reality. Here's an example. For people with color vision, like me, I sort of feel like, oh, I'm looking out at the world and I'm seeing everything. But in fact, we know that about 10% of females have a fourth type of color photoreceptor. So instead of the three that most people have, these minority of women can see colors that the rest of us aren't seeing at all. And that means that to them, I'm essentially colorblind. There's parts that I'm missing. They can discriminate two colors that would look identical to me. So it's easy to see how we all take our reality as presented to us. An interesting note here is that sometimes people will ask me, well, wouldn't it drive someone crazy to be a synesthete where, you know, every time they're hearing music, they're seeing colors and all these colors are everywhere. But it would be the same thing if a colorblind person asked you, doesn't it drive you crazy to see colors everywhere you look?
Isn't it just too much?
Exactly. Yeah. The answer is that's what we take the world to be.
So let's back up just a little bit. You mentioned earlier that we need to have our biology intact. So we need to let's talk about the state of the brain and how the brain exists in our body and the job that it has in creating the world that we live in terms of deriving the questions that you're asking about how we perceive what we perceive.
Yeah. Well, about 120 years ago, there was a young railroad worker named Phineas Gage who got a tamping rod that went through his head, a metal rod that went through his head. And it's a very famous case. Most people know about this now. The reason it's a famous case is because he didn't die. It was a very bad head injury, but he didn't die. In fact, he didn't even lose consciousness. But what did happen is it changed him entirely. And this was the first sort of very clear case that you are dependent on your biology, on the integrity of your biology in order to, you know, be who you are. And in the intervening 120 years, we've had lots and lots of Phineas Gages. The medical literature is full of very specialized, very carefully studied cases now where somebody's brain changes and it changes them. So
I'm a huge fan of Oliver Sacks, by the way. He does a great job of describing a lot of these medical cases.
Exactly right. And if you take all the cases that Oliver Sacks has described, that's maybe 0.01% of the number that are in the literature that are interesting like that. So it's because of these brain damage studies that we're able to identify what parts of the brain are involved in different types of issues like decision making or seeing color or understanding language. Now, all we can really say from brain damage is that the integrity of those areas is necessary for that function. It does not mean that the function lives in that spot of tissue. It just means that that tissue is necessary. In the same way that you could bomb the runway to an airport and find that there are no planes leaving, but it doesn't mean you hit the airport. It just means you've messed up the system. Okay, so, but it's because of you know, a century of that, plus in more modern times, non-invasive neuroimaging, which in many cases confirms which areas are involved. And you know, as we become more sophisticated, we move away from thinking about things as involving an area of the brain, and we understand them to involve networks in the brain, usually very widely distributed networks. But nonetheless, this is how we can tell that these different parts of the network are necessary in order for you to be able to do what you do, and you take it for granted. So let me just say one more thing on this, which is, the easier something seems to you, like, oh, I just opened my eyes and there's the world, what that really means is the more sophisticated neural machinery that you have that's devoted to that process. So in other words, the more machinery you have under the hood, the more effortless you think the issue is. Right. But when we examine it, we find, you know, a third of the human brain is devoted towards constructing vision. And the only way that we ever come to understand the machinery and the effort behind this is when we look at things like brain damage or when we look at things like visual illusions. So normally trying to understand vision is like asking a fish to describe water. We've never experienced anything other than that, so it seems like it's very natural. Just in the same way that a fish wouldn't have any capacity to describe water because he's never seen anything otherwise. But when a bubble comes up past the fish, then the fish can say, wow, something weird happened. Well, that's what visual illusions are like for us as neuroscientists. We say, hey, that's strange. Why would the brain put this together or that together? And then we start examining it, and it allows us to tease it apart.
In terms of the teasing apart, I'm curious about the timing of how the brain puts everything together. There's a standard test. You touch your nose and like your hand or your nose and your toe at the same time, and your brain registers those things as happening at the same time. However, the information from your toe had a lot further to travel to get to your brain than the information from your nose. So there's something going on within the brain to balance everything out. Do you have any insights in how that works?
Yep, I've spent the last 10 years studying that exact issue, actually. The challenge that the brain has is that it's encased in silence and darkness in the vault of your skull. And the only information it gets are these electrical signals that come streaming in through your different sensory systems. So through the eyes and the ears and the fingertips and the sensory sheet of skin and your internal organs. All this information is coming streaming into the brain on these specialized cables along your spinal cord or the cranial nerves. But the brain has this very big challenge of trying to figure out what actually happened when in the outside world. So, for example, a signal from your toes takes a long time to get all the way up your spinal cord to the brain, whereas a signal from your nose gets there almost immediately. And so somehow the brain solves this problem, and I have, in the last 10 years, been able to determine how the brain solves the problem. And the answer is it waits for the slowest information to arrive. So you're always living in the past because your brain has to collect up all the information coming in through these different sensory modalities and stitch together what it considers the best story about what just happened out there. And once it's put that story together, then it serves that up to you and you have a conscious experience. But what that means is that your conscious perception is like a live television show, like Saturday Night Live, which is not actually live. It's aired with a delay. And that's what your waking life is like also. You are living with a delay to the real world. And the reason it has to be this way is because of the amount of time it takes to get information to the brain.
I read somewhere like a year or so ago, somebody came out, there was something that was like, we live 0.25 milliseconds in the past, or it was like half a second in the past, or something. They'd basically done an analysis of all the different, or what is the slowest thing that gets into that your brain is having to process, and with your visual system plus your auditory system plus somatosensory and everything. I don't remember the exact number, but they had tied it down. So everybody's going to be living X amount of time in the past. Is that true, or do you think there's a difference between individuals on how far in the past they're living?
Well, the estimate is 500 milliseconds, and it's actually not it's half a second, and it's actually not a new estimate. It's quite old. It was from the 1970s, where there was a scientist named Benjamin Libet who collaborated with a neurosurgeon who was putting electrodes into people's brains during surgery. The brain has no pain receptors, so you can insert an electrode without any hurting of the patient, and then you're able to measure what's going on with the electrical activity there, and you can also stimulate electrical activity there. And it was this sort of complicated experiment, so I won't describe all the details, but I will point people to the papers of Benjamin Libet, L-I-B-E-T, if they're interested in this. But what they concluded is that you're about 500 milliseconds in the past before you have conscious awareness of something. Now, the philosopher Daniel Dennett has made an argument since then saying, look, it's actually impossible to know exactly how far in the past we live because it's impossible to nail down the moment at which you become conscious of something. And the reason that's impossible is because if you're doing a reaction time experiment where you just hit a button, for example, your motor reaction times and your conscious awareness of something, those can actually be decoupled. So, for example, you can react to something faster than you're consciously aware. So there are all sorts of problems there. Maybe I won't go into the details here, but Dennett argues you can't exactly know how far you live in the past. Nonetheless, the best estimate on the books is something like half a second. I do think that there are differences between people. I have long suspected that, just from anecdotal evidence that I've collected, suspected that maybe couch potatoes and high-performance athletes might have time doing very different things in their brains. If you're a professional martial artist, you are dealing with things in time at a faster level, and maybe you know how to ignore, maybe not wait for certain signals to get there before you react to other signals. It's also the case, I've been thinking about this for a long time, and I haven't been able to run this experiment yet, but I'm going to finish it by the end of the summer. I've had a hypothesis that tall people probably live further in the past than short people. Because for a tall person, if the brain is going to wait for all the information to get there, the slowest information is coming from the toes.
Right.
And so the brain would get used to waiting that long. Whereas for a short person, the brain only has to wait for a shorter window of time.
But maybe taller people have a faster processor speed in the brain once they get the information. So to make up for that delay, is there maybe some kind of compensation?
I don't think there could be, and I'll tell you why. Because the whole delay is the signal conduction coming up the nerves, right, coming up your leg and climbing all the way up your spinal cord. And it turns out that the speed of propagation of these signals up these nerves is the same for everybody. So I think that's the main delay that the brain has to deal with, is actually receiving the information.
I'm thinking of another thing here. So going into time perception, as people get older, they tend to experience time going faster because their brain has experienced things already. And so you don't have to pay attention to, your brain doesn't pay attention to and lay down all the details of a memory all the time. Whereas when you're a kid, everything takes forever because your brain is just taking in and soaking up all the information, and it's doing a lot of work. Maybe that's something similar for people who are tall, that they're tall and they've gotten used to certain information, so that after a certain amount of time, maybe as you're growing and you experience things, that compensation happens, and so there are multiple outcomes that your brain is ready for in that information, which is why the experiment should be done. You should figure it out.
Yeah, that's right. The truth is, I suspect those are two totally separate issues. So the issue you just mentioned about how time speeds up for people as they grow older, and the hypothesis that you expressed about why that happens is actually what I've been working. So that is the hypothesis that I've been suggesting for the last year or so, because we've done other experiments to show that the more densely you lay down memories, the more you think something took a long time. And if, on the other hand, you're not really laying down any dense memories, it seems to have passed quickly. And so what happens, as you alluded to, for a child, they're trying to figure out the rules of the world, and they're writing a lot of things down. They're forming new memories at a large rate. And so at the end of a childhood summer, it seems like it's taken a long time. Whereas at the end of a summer when you're an adult, it seems like it's zipped by because you're doing all the same things and you don't have any new memories laid down. But all of this applies at a much longer time scale. Right. So the issue with tall and short people is all at the sub-second time scale. It's about what we call the immediate perception of time. So whenever you're doing things like, okay, which came first? Let's say I hit a button and a flash of light happens, and I'm trying to decide, did I hit the button first before the flash, or did the flash happen just before I pressed the button? Things like that have it's like a sensation of time. as opposed to a more cognitive looking back at large stretches of time, as in children and old people.
Right. I'd love to have you explain some of your exciting time perception studies that you've done recently. In the literature and also in the popular media, there have been stories of you telling people to jump off of a tall tower in the name of science.
Well, that's true. Yes, well, one of the things that I've been trying to do is figure out, how brains encode time, really what's going on in the neural machinery. And one thing that was confusing me for a while was I heard reports from people, and actually I had experienced something like this myself, of time seeming to slow down during a really fearful situation. So, for example, people get into a car accident and they say, oh, it seemed like it took forever. All these things happened. I saw this piece of the mirror fly off. I saw the hood crumple, things like this. And I needed to know if that was actually true. Can time actually seem to move in slow motion? In other words, does the brain have some sort of turbo boost mode that it can go into where it's taking in time at a different pace somehow? And this had happened to me when I was a child. I fell off of a house that was under construction, and I fell all the way to the floor and landed on my face on the floor. Wow. And broke my nose very badly, and I was unconscious for a little bit. But the fall itself, I remember very clearly, and it seemed like it took a long time. I was thinking thoughts on the way down. And when I got to high school and learned physics and did the calculation, I realized that the fall had only taken me 0.8 seconds. So I was trying to figure out how that could have been. So I looked in the literature to find out, how would you know if time can be perceived at a different rate in a high adrenaline situation? Well, not surprisingly, no one had ever addressed this question. First of all, because the time literature is very small. I'm one of the only labs that studies time, and no one had ever thought of how you could actually put people into a fearful situation that is totally safe.
Right. So put them into a safe situation, but at the same time have that fear response still lay down the memories somehow. Exactly.
So what I did is I took my whole lab to Astroworld, which is the amusement park here in Houston, and we went on all the best roller coaster rides and all the scariest rides, and we brought all our equipment with us and stopwatches and various things that we developed and invented. And it turns out that none of those rides were scary enough. Even when you're on a really scary roller coaster, you don't think that time moved in slow motion. So I had to find something even scarier. So with my student Chess Stetson, we went hunting for the scariest, safest thing we could find, and we found something called SCAD diving, which stands for Suspended Catch Air Device. And the thing with SCAD diving is it's a tower that's 150 feet high, and you take this little cable elevator to the top of that, and then you drop from that elevator, and you're going in free fall, and you're falling backwards, and you're going 70 miles an hour when you're caught in a net below.
Oh my gosh.
So it's absolutely terrifying because you're falling backwards, you can't see where you're going, and you're in complete free fall. And it turns out this was sufficiently scary. And I did the jump myself 3 times, and my graduate student did the jump 3 times. And, we made sure that it was very safe. And then we spent several months getting this approved by the ethics board for us to do this.
Yeah, I'm just wondering, once you got it passed, finding people to jump, that you have to be a thrill seeker in the first place, right?
Well, that's probably right. And fortunately for us, what we discovered is that even for thrill seekers, they get this time distortion effect where they think that the fall lasted longer. And the way we measured that is first we have everybody watch. So first you start off, you watch someone else fall from the tower, and then retrospectively you time with a stopwatch. You figure out how long you think that took. Then you do your own fall from the tower, and with a stopwatch, you retrospectively say how long you think your own fall took. And exactly as we suspected and as we experienced also, when you're judging your own fall, you think it took much longer. You remember the fall is lasting longer than it actually did because it's really scary. So, but here was the interesting part of the experiment. We built and patented a device called the perceptual chronometer. And in the lab, we called it the Eagle Eye. But what it is it's essentially a wristwatch that you strap to your wrist on the inside here, and it flashes numbers at you in a particular way. So if you imagine a grid of LED lights, and these lights can spell out different numbers, right? So let's say you have the number 38. What happens is every instant, the lights that are on go off and lights that are off go on. So you're alternating between a positive and a negative image of the number 38. And it turns out that if we alternate the positive and the negative images at a particular speed, you can read it just fine. But if we speed it up just a little bit more, the alternation rate, you can't read anything. It looks just like flat LEDs, and you can't distinguish one number from any other number because it's going too fast, the alternation back and forth. So with this device, we're able to measure how fast people are seeing the world, because the idea is if we were alternating between the positive and the negative images at a particular rate, and then we speed it up so that it's too fast for you to see the different images. But now, if you actually see the world in slow motion, you should have no problem reading the different images.
Right.
In other words, if you're like Neo in the Matrix and you're seeing in bullet time, then you would be able to read numbers on this device that you couldn't read under normal circumstances. So that's what we did. And we tested 23 people. We found 23 subjects who were willing to take this fall from the tower.
College students will do just about anything.
That's right. Although we had all ages and genders, it was a pretty good mix of people. And what we discovered is that people cannot see like Neo in the Matrix. So even though they think the event lasted longer, they're not actually seeing in slow motion. So this seems like a paradox, right? It seems that it seems impossible. But this is how we first started really getting clear on the idea that time and memory are intertwined. And so what happens when you're in a fear for your life situation, a part of your brain called the amygdala comes online and lays down memories on what amounts to a secondary memory track. And those are very dense memories. Fearful memories are essentially the best memory machinery that you have. Yep. And it turns out that because your normal memory systems are very leaky, and because your fearful memory systems make everything stick, as a result, when you look back on it, you think, my gosh, I was thinking this, I noticed that, I caught that detail. And so the only thing that your brain can make of this is that it must have lasted a long time. Your brain thinks, wow, if I noticed this and this and this, it must have been that time was moving slowly.
So what's happening is that people can judge the time of the fall fairly accurately looking at other people falling. But then when they're actually remembering it, their memory is altered because there's just a lot more information for the brain to be dealing with. And so, like you said, just you think it took longer, where the actual fall did not take long. Your brain did not process it differently, so to speak.
Yeah, that's exactly right. So it has to do with the density of memories that you lay down.
I wonder if, has anybody looked at time perception in terms of coffee or stimulants in any way? A lot of people talk about, feeling like things go faster. They're able to process things differently. And I know, in performance enhancing drugs in the pharmaceutical industry are potentially going to be something that people are going to be looking at as we move into the future. Is this, do they actually affect, would it be something in where it's our memory of the event that's affected more so than the actual event?
Good question. It's hard to know what the thing is that's affected. People have done animal studies on this. For example, my colleague Warren Meck does studies where he trains a rat to hit a lever at exactly 10 seconds. So a beep goes off, and then the rat has to wait 10 seconds and then start pounding on a lever to get the reward. And if the rat starts hitting the lever too soon, he doesn't get the reward, and so, or too late, the same thing. And so rats can pretty quickly learn up a 10-second duration. Okay, so now he puts the rat on marijuana and finds that now the rat hits the lever at 13 seconds instead of 10. Or he puts the rat on cocaine and finds that the rat hits the lever at 7 seconds instead of 10. So it's a little hard to know what's going on inside the rat's head. And I haven't run these experiments myself in humans because it's actually quite difficult to get approval to do drug studies in humans, which is a little bit of a shame because there are plenty of people using drugs, so it'd be terrific if we could study them anyway. And of course, all over Europe, scientists are allowed to do these sorts of studies. We're a little bit hampered by, I think, a slightly puritanical governmental attitude here in America when it comes to drug studies.
Yeah, because there's no way you can actually ask the rat what was going through your head before hitting the lever in these different situations.
You can certainly ask the rat, but you won't get a good answer.
Squeak. Squeak. Not a great answer at all. Yeah, it seems, people always, it's the perception side of it. People always talk about you taking performance-enhancing substances of any kind, even chocolate, whatever it happens to be that you're taking into your body that affects the way that you perceive your environment, your world. You think it changes things, but what is it really changing? Is it that that pot just makes you go, whoa, there's a lever. Supposed to do something with that lever. Oh yeah, I'll hit the lever. Does it just slow everything down that way? Is it cocaine that says lever hack? Got it. What is going on there? It's too bad.
Yeah, that's exactly the right question to ask. And with animal studies, you have to ask these questions about is it just a motor issue? Maybe you're just slowing down the motor system of the rat in marijuana, and so yeah.
Yeah, is it the brain? Is it the motor system? What is getting slowed down?
Yeah, exactly.
Yeah. So, what are the questions that are really still open to be answered? The big questions in terms of how our brain helps us perceive the world. As you look at the problem.
Well, a shorter list would be the problems that we have answered already. The long list is the questions to be answered. At this point, we know a lot about the anatomy of, let's take the visual system, which is the best studied sensory system. We know a lot about the landscape of it, and yet we don't even know the basic mechanism by which vision is constructed. Here's the wrong way to think about vision, which is in every single textbook. What's in all the textbooks is that photons hit your eyes, and that causes electrical activity which goes through the middle of your brain over to your visual cortex on the other side of your brain, and then you have successively complicated stages of processing, and eventually you see. Well, it turns out that's completely wrong, because the way vision actually works has to do with all of this internally generated activity that's going on all the time in your brain internally. And of course, you can see that because you don't even need your eyes to see. When you go to bed at night and you sleep and you dream, your eyes are closed and yet you're having full, rich visual experience. And it's exactly the same processes that are going on, except they don't have anything to do with your eyes. And of course, if we put you in a sensory deprivation chamber where you're floating in warm water and there's no sight and no sound, you'll quickly begin to hallucinate and see things because the only thing that having your eyes open does for you is that the little bit of data that dribbles in through these two holes in the skull, it merely anchors the activity in your brain. So in other words, your brain has visual action going on all the time, and when your eyes are open, those merely modulate the activity going on in your brain. So I think it's fair to say we know that much is true, although I don't think that's widely appreciated in the neuroscience community. But for people who really study vision, that part seems clear. But how exactly that works and how we would make a computer that runs the right algorithms so that it could see, we don't actually know how to do that yet.
I think that's a very interesting question, how to, I guess, reverse engineer what we already have naturally. What are the all the different pieces of information that would be needed to create the algorithms that would run that computer? And it's got to be highly complicated.
Well, yeah, and of course that's the only way that we ever know if we've got the right answer, is if we can build it ourselves. And so once you can build an artificial brain or even just an artificial visual cortex, then you'll know that you're on the right track. But we can't do that. Not even close yet.
Right. There's someone in the chat room just just made the statement. So the visual cortex is a party, and the eyes are the cops that show up to ask to turn the volume down.
That's terrific. Well, yes, thank you. In fact, if you could ask that chat room member to give his or her name, I'll make sure I quote the name when I cite that in the future.
Excellent. I believe his name's Jeremy. In the chat room, his GL Disater, Disater. Okay. But yeah, I think that's a great analogy of how it works. That's something that a lot of people have brought up, from going way back, is that we have constantly there's massive amounts of information coming at us from everywhere. There are photons of light. There is physical, mechanical energy hitting our body. There's sound waves. There are all these things, odorant molecules, chemicals in the environment. Everything around us is constantly affecting us, and our brain is in effect a filter.
That's that is one way of looking at it, but I don't even think that's I'm not even sure I think that's totally right. Most stuff doesn't even get in there at all, and it's not because of a filtering process. It's because your brain doesn't even think that it needs it. So it's not like, let's do it this way. It's not that information is coming streaming in and gets filtered out. It's that most stuff doesn't even get very deep in there at all. Here's what I mean. So you have all the internally generated activity where your brain essentially feels like, okay, I know what's going on here. And the only time your brain ever starts paying attention to the external stuff is when it needs to know something. So for instance, if I ask you what is the position of your tongue in your mouth right now, you can answer that question. But you didn't know the answer to it before, even though the sensory data was there, because your brain just doesn't need it. I'm only making a slight modification to what you're saying. It's not that it's filtering it. It's that it's not even asking for it. It's not even asking for the information. And of course, if you were to, if I were to ask you, how many books do I have on the bookshelf behind me? Those have been sitting on your retina the whole time. But all your brain needs to know is, oh, well, there are books back there.
Right.
And it doesn't need to know anything past that until it's challenged and there's a sufficient reward and motivation for answering it. And then it starts paying attention to the external data. But for the most part, it's perfectly content to say, okay, well, it's some guy sitting in an office with books behind him.
Now, I'm curious to know what you're going to be doing soon. I want to keep this conversation going forever and ever. This is so interesting. But unfortunately, we're getting to the end of the hour, and I promise to keep you to your time schedule because I know you have to go write books. You have deadlines to reach. For people who are interested in finding you on the internet, for going to one of your lectures, are you on a lecture schedule that people could actually hear you speak publicly?
Yeah. Eagleman.com is my website, and it has my entire lecture schedule on it.
Right.
And I'm in essentially a different city every week doing something or another. So it would be terrific. Come join me and let me know that you saw me here on drkiki.tv.
Yeah, that would be great. I'd like to know that too.
I'll let you.
If anybody comes up to you randomly out of an audience, let me know.
I will.
It would be great. Yeah, so like David said, Eagleman.com is his website. And you can also, as I mentioned earlier in the hour, he is a fiction writer as well as a scientist. And he's written a book called 40 Tales from the Afterlives, which we didn't even touch on this hour, but is a very interesting and entertaining read and has gotten pretty critical acclaim from many areas. A lot of people are very excited about this book.
Thank you. Yeah, it's been a great surprise for me. In September, it became the #2 book in England, and just behind Dan Brown's Lost Symbol. And that's an incredible surprise for a neuroscientist who's writing fiction just as a side thing. It really went well, and it's been turned into musical performances now at the Sydney Opera House and the Brighton Dome. And in 2012, it's getting turned into a full-fledged opera at the Royal Opera House in London.
Wow.
And so it's really blown up into something that's much bigger than I could have ever envisioned, and I'm very happy about that.
You should be. That's really exciting. That's great.
Thank you.
Well, thank you so much for joining me today. This has been a lot of fun to speak with you and delve into your research and talk a little bit about something that we all have in common, which is our brains.
Yes.
Yes. We might not have the way we perceive the world in common, but the fact that we have brains, we have that in common.
Yes.
Yeah. So
Okay.
Thank you very much. I won't keep you any longer. I appreciate your time and have a wonderful rest of the summer. I don't know if you're back into a teaching schedule at this point or not, but with your research and everything, good luck.
Thanks, Kiki. Good to see you.
You too.
Bye.
Thanks. Bye. And that was Dr. David Eagleman. He is a professor at Baylor College of Medicine. He, like I said, you can find him at eagleman.com. and find out much more about his endeavors, what he's into. You can also see him speak. I believe he gave a TEDx talk, TEDx Houston. He gave a talk, and he's on the web. He's done some stuff. He's part of the Long Now Foundation, and he's got his fingers in all sorts of little pockets. Very interesting pockets, actually. So he's someone worth looking into and finding out a little bit more about. He's got some big ideas. Next week, we're going to be talking about the Science Commons with John Wilbanks of the Creative Commons Science Commons. So we're going to be talking all about that next week. Until then, you can find my sciencey pursuits on the interwebs just by Googling for Dr. Kiki. I'm Dr. Kiki on the Twitter, on the Facebook, on the email, and, my website, drkiki.tv. If you want to download and view old episodes of this show, listen to audio of old episodes of this show, you can do that at twit.tv/Kiki. Additionally, I will send you to the newly launched Green Tech Today, in which Sarah Lane and I talk about green technology and a whole bunch of other stuff. We have a great time. The first episode just came out last night. We're very excited and proud of our efforts. So we hope that you enjoy it. Go check it out. It's in iTunes. It's also on the twit.tv website, twit.tv/GTT. That's Green Tech Today. If you have any questions, comments, ideas, like if you have a question for John Wilbanks about the Science Commons, you can actually call me. You can leave me a voicemail that I can play on the show. The phone number is 650-741-KIKI. That's 650-741-KIKI. It's a Google Voice account. You'll be able to leave a message. And if you want to comment on the show, leave a question for John Wilbanks for next week, go ahead and do that. Or send me an email, Dr. Kiki, or what is my email? drkiki@twit.tv. I think that's what it is. Yes. So I'll see you next week. Thank you very much for tuning into my Science Hour. And if nothing else, I do hope this hour made your world a whole lot more interesting. Go think about it.